Hi, in the last couple of videos, we learned about homogeneous functions and their application to the production function. However, one of the main results we established there is that homogeneous functions are creating for us expansion paths that are linear. And the question is it the property only of homogeneous functions? As it turns out, there is a broader group of functions that possesses the same property. And this group of functions are called homothetic functions. So how do we get this homothetic function? Let's say that h will denote our homothetic function, and this, if we have a situation where this is a function of q, where q is homogeneous production function of degree r. Okay, and it turns out that if we will have that h prime of q, so derivative of this function with respect to q is different than 0, we get a homothetic function, and it's going to produce for us linear expansion paths. However, there is one thing we should take into consideration here. If we talk about economic applications, we would prefer for this derivative to be bigger than 0, which actually gonna turn out pretty self-explanatory once we get into the examples. However, how can we be sure that this function, this homothetic function, is going to give us linear expansion path? Okay, and actually this is a very easy process. There is a very easy couple-step process to prove it. Because look, we see that slope of the isoquant h. So if we would like to calculate isoquant for this function, what do we need to do? Well, the slope of this isoquant is going to be equal negative hl, which is derivative of function h with respect to labor, divided by the derivative of function h with respect to capital. However, we can easily find these derivatives using the chain rule, because first we need to in the numerator we need to differentiate this expression with respect to L, right? So we will get QL, and we need to multiply it by h prime of q, right? This is how we are going to get we're going to get expression for partial derivative of h with respect to L. And look, now similarly, we calculate the derivative of h with respect to capital, which is giving us qk. Right away, we can see that those two are canceling each other out, and what we get is the slope of the isoquant for q. So we clearly see that they will have exactly the same slopes. And now look, then we can conclude that as long as q negative QL, QK is constant, then, of course, this expression must be constant as well. So, with constant slopes, we can get the same capital to labor ratios, and we will be able to get an expansion path that is linear. Okay, so this is the first of the two main nice properties of homothetic function. The second is actually associated with the elasticity, with the elasticity of capital to labor ratio with respect to changes in the level of production. Because look, if we have established that this expression is constant and this expression is constant, it means that capital to labor ratio is not going to be affected by changes in the level of production, right? This is where we get the linear expansion path. However, we can write it as derivative of capital to labor ratio with respect to production, changes in the level of production, is 0. Right? So, working with this result, we can actually get to something a little bit more profound. So, okay, so in the next step, let's just change this lowercase k into the capital labor ratio. Okay, we see right away that in this case, we need to use the quotient rule. So, first, derivative, a function in the denominator to the square times expression at the bottom times derivative of the expression at the top, and then of course minus expression at the top times derivative of the expression at the bottom. Okay, so now let's rearrange this expression. First, I'm going to multiply both sides by L squared times H0. Okay, so look, right away we are able to get rid out of this, right, which is not very necessary over here for us. We know that this is actually different than 0. And as a result, we are getting H0 times L times derivative of K with respect to level of production, and similarly over here, just in the other order. Okay. So the next thing we need to do is to change this L into 1 over K and change this K into 1 over L. Well, how can we do it? Well, all we need to do is to multiply both of these expressions by 1 over L times, right? So look, now L is gone, right? And K goes to the denominator, and we get expression like this. And similarly over here, And we're gonna have, let's already move this expression to the other hand side of the equation. And again, here k is gone, L goes to the bottom. And we get expression like this. So now the question should be, what actually this expression is? Look, here I could say that this is a quotient, right, of the marginal function to the average function if we would reverse, right, for a quotient. So what we get on the left hand side is the definition of the elasticity of the optimal capital with respect to production. And look, in a similar fashion, we can see that this is the elasticity of the optimal labor with respect to production. And what we see is that in the case of homothetic functions, we get that these elasticities are equal to one another. Again, this result should come as no surprise, as this function actually produces linear expansion paths. Okay, but we talked about theory quite a lot. Let's now maybe try one example to see how it actually works. Okay, so let's just say that the function we are going to have is h equals q squared. And let's just say that our q squared is a Cobb-Douglas production function. Okay, so first, right away, I can just substitute and take this function to the power of 2. See what am I getting? So this is a squared times L to alpha k to beta. And look, in this case, we can also say something about economies of scale, right? If we increase the level of labor and capital by some factor j, level of production is going to increase by 2 alpha plus beta. Okay. Now, let's go to the slope of the isotope. So in this case, we should calculate negative HL over HK. Okay. So let's do it. So here the derivative is going to be 2 alpha x squared L to alpha minus 1 k to the power 2 beta divided by 2 beta a squared L to the power 2 alpha k to the power 2 beta minus 1. Well, we see that 2's are canceling each other out, a squares are canceling each other out. We again see that this part and this part are canceling each other out. So at the top we've got L to the power negative 1, which means we need to bring it into the denominator, while here we've got the opposite situation because we've got k to the power negative 1 in the denominator, so it's going to move to the numerator. And look, what we got, what we get over here is alpha over beta times k over L, or simply alpha over beta times k. And again, we get the result where we can actually find what is the optimal capital to labor ratio, as long as we know prices of capital and labor, and it's gonna remain constant. that the properties of homogeneous functions that are very interesting and important in economic context can be quite easily extended to a more general class of homothetic function. However, there is one more property that we should discuss, and this is going to be elasticity of substitution of capital with labor. Because of course, when prices of capital and labor are going to change, we would expect that the companies would change the proportion of capital and labor they are using. And if they are doing so, maybe we should somehow calculate and describe how they are doing, and this is going to be the topic of our next video. Thank you for your attention and take care.